In this video, we're going to be looking at one of the most important applications of integration, and it's called the volumes of solids of revolution. And right now it says the wash method, but we're going to be looking at both of them at the exact same time. So I'm going to include here washer slash shell. And I like to teach both of them at the same time because of the strategy that I have. And it's very easy to distinguish between the two. So what's the objective for this video? You're going to state the washer method slash shell method. Okay. And the second one is find the volume of a solid using the washer method or the shell method. A lot of professors teach them one at a time, but I like to teach them both at a time. Okay, so let's go ahead and visualize what a solid revolution is. A solid revolution is really going to be some area, and in this case we're looking at the area of what's underneath this curve. All right, so what I'm going to do is I'm going to take that curve and I'm going to revolve it. So that's why they call it a solid of revolution. So let me bring out the PowerPoint, and on the PowerPoint it's a lot easier to see that visualization. I'm under OneNote. So what I have here is I have the area underneath the curve, and we're going to take this area and we're going to revolve it around the y-axis. So when I revolve it around the y-axis, that is going to give, oops, that's one piece. I need to show you the PowerPoint for this one. That's the wrong PowerPoint. Here we go. Okay, so I have this area, and I'm going to take this area and I'm going to revolve it around the y-axis so you guys can see exactly what it's going to look like. So I'm going to take that area and it's going to get revolved around the y-axis, and it's going to be creating some kind of a cylinder with a what would you call it, a gumdrop hole inside. Okay, so that's a solid revolution. Now the area can also be revolved around, around the x-axis. So in this case, what we're going to do, instead of looking at the whole area, we're going to be looking at rectangles, just like Riemann sums. Riemann sums uses one rectangle to estimate the area underneath the curve. What we're going to do is we're going to estimate it by revolving only one rectangle around it. So let's go ahead and that rectangle here, I created a rectangle which is lying flat. It's perpendicular to the x-axis. So what happens when I revolve that one around the y-axis? Remember, I'm revolving the whole area, but I only want a section of it. When I revolve it around, guess what we notice? It creates some kind of a washer. So if you look at it, it's a little washer that a lot of people, mechanics, use on the screws. All right. So that right there is what we call the washer method. So let's look at another method here. Now in this case, I'm going to take the area underneath the curve from this curve to the x-axis, and I'm going to be revolving it around some line y equals -2, y equals -3. So let's go ahead and look at this one. But in this case, I'm revolving 4 rectangles, and if you notice, it's going to create 4 different washers. Now I don't worry about the number of washers, because remember, the thinner the dx is, in this case, the more what can you say, the approximation is going to be closer to the exact volume. All right, so now what happens if somebody says, hey sir, let's do the rectangle up and down, but I'm still revolving it around the y-axis. So if I revolve it around the y-axis, it creates some kind of a straw. But that straw in mathematics is going to be called a shell. Okay, so it still looks like a cylinder, still circular in motion, right? So let's look at this one over here. In this example here, I'm going to take this one and I'm going to revolve it around the y-axis again. So here we go, around the y-axis, and it's going to create a bigger straw. Okay, now what you need to understand is, in the washer method, in this method here, if you notice a rectangle and the axis of revolution, they're perpendicular. But if you look at the shell method, here's my axis of revolution and here's my rectangle. They're going to be parallel. So if you notice that ELL on, well, the LLL here on shell, it's going to mean parallel. Okay, so let me go back to my presentation here. All right, so the washer method, if you notice, here's my rectangle and here's my axis of revolution, and what do you notice about the two? That this, if I was to extend this is perpendicular to this. So the washer method is going to be perpendicular to the axis of revolution. Okay. The washer method, okay, let me show you the washer method. Here's my axis of revolution and here's my rectangle, and what do you notice about my rectangle, the height of the rectangle and my axis of revolution? They're parallel. So here's going to be parallel, oops, parallel, and if you notice the double L in shell, that's going to be a clue for us. Okay, so here's the strategy, right? How do you find the volume of solids of revolution? Number one, draw a rectangle up and down. 99% of the time that rectangle is going to be up and down. Okay, so it doesn't matter if the axis of revolution is up and down or the axis of revolution is like this. If it's like this, it's going to be washer. If it's like this, it's going to be the shell. That's it. Now the 1% is the unique one. The 1% is when you have a function that looks like this. Okay, so let me go ahead and do this, and we're going to be talking about the area here. If I was to draw a rectangle here and here, what do you notice about the rectangle? It's using the function and the function, so it's very hard to find the height of the rectangle when it's touching the same function. So we have to make sure that my rectangle is lying flat. It has to. That's the 1% of the time. Okay. Now, step one is draw the rectangle. Step two is highlight the axis of revolution. Now, why are these two steps important? This one's going to determine step three. Okay. Step three is which formula am I going to use? Is it the shell or is it the washer? Well, if you do step one and step two and you draw them like this, that's telling you that it's going to be the shell. If you do it like this and like this, that's going to tell you it's going to be the washer. Do you see how important that is? Now, here are the two formulas that you need to understand. Remember in our visuals how we're going like this or we're going like this? You know, if my axis is there and my axis is there, they both create circles when you revolve it. That's why it's very important that we use pi here, and on one of them we're going to be using pi r squared. So this is what we use for the washer method, and 2 pi r is going to be the shell method. Okay, now some people are going to say, sir, why the difference? Well, in one of them you're going to be creating some kind of a disk, right? And in this disk you're going to be using pi r squared, which is a circle. So you're really looking at the area of that circle, and this is my dx. In the other case, you're going to be creating a shell, and in the shell we're going to be using the lateral surface area, which is going to be 2 pi r h, and that is going to be very important. So if I cut it down the middle here, if I cut it down the middle and I open it up, is going to create a rectangular prism here like this. And basically this is my dx, and this is the height, and this is my 2 pi r. So it's 2 pi r, which is my circumference, times the height, and that is going to be the shell method. All right, so here we go. The wash method is going to be pi big radius squared minus little radius squared, and the shell is going to be 2 pi r h. Now some people are going to say, hey sir, where did the other radius come in? Okay, so when I make a washer, here's my washer, and here's my axis of revolution. Here's my axis of revolution. Go like this. You're gonna notice that this distance here is gonna be my little r, and this distance right here is gonna be my big R. So my washer is gonna have a little r and a big R. Now, what happens if there is no inner circle? Okay, and that's a very important question, because some people they consider that to be a topic all in itself. If there's no inner circle, that means that your little r is going to equal to 0, and your big R is going to be this. It's going to be that guy right there. So this is called the disk method. Some people spell it like this, and some people spell it like this. I will go this route. Okay. So the disk method, you're just going to say the little r here is going to be 0, and 0 squared because it's touching it. The little right here, this guy is touching it, and if it touches, that means that little r is 0. And if little r is 0, I'm going to be left with this formula. The disk is going to be pi big radius squared minus dx, and that's it. So the disk method is really the washer method, except that the little radius is r. All right. Now, you need to understand, when you look at these two formulas, what are the letters that you see? Well, you see a big R, you see a little r, and you see an h. So here's my big R, here's my little r, here's my little r, and here's my h. Those are the only variables that you're going to have to really understand. Okay. Now, if you have two radii, okay, or the radius and the height, you only really have to worry about two of them. Okay. So here you're going to notice that there's going to be a big R and a little r. Here you're going to have r and the height. R is always defined. Did you hear what I'm about to say? R is always defined from the distance from the rectangle to the axis of revolution. Now, if there's two of them, if there's a big R and a little r, because it's a washer, the small radius is going to be the closest distance, and the big radius is the furthest distance. Okay? Now you're going to say, I don't understand, so what you're saying. Okay, so let me go ahead and come over here. All right, here's my axis of revolution. Let me go ahead and go around like this. Here's my washer. Okay, please don't make me so exact. Okay, so right here, this distance is going to be the closest distance. This is my axis of revolution. This right here is my axis of revolution. And where's my rectangle? You're saying, where's the rectangle? So the rectangle is going to be right here. Here's my rectangle. And I'm taking that rectangle and I'm revolving it around the y-axis. So this distance here, he's going to be my little r. While this distance from here to here is going to be my big R. Okay? So the little r is the closest distance of the rectangle to the axis of revolution. Big R is going to be the furthest distance. Okay? And then in the washer method, though, you only have an R and an H. You have an R and an H. The R is still going to be defined as the distance from the rectangle to the axis of revolution, and the height, H is going to be the height of the rectangle. And how do we do that in in areas between the curves? It's just going to be the top function minus the bottom function. Top minus bottom. And that is always going to be my height. Okay? Now, students had difficulty, when they had to subtract and when it was in the negative. So I decided to bring in what I call the little man. Okay? And the little man is always going to stand on the x or y axis. Did you hear what I said? Not the axis of revolution. Well, it could be the axis of revolution, but he's always going to stand on the x or y axis. Okay? And he always walks in a positive distance. There's no way you can walk a negative distance. So he's always going to walk positively. If he walks up and down, he walks y. If he walks left and right, he walks x. That's the only concept you have to remember. So if he is here and he walks this way, he's walking x. If he is here and he walks this way, he's walking y. That little man is very, very important. Okay? So let's go ahead and and look at some examples. And in these examples, I decided to write everything down because as I speak, you might not understand what I'm saying. Step 1, draw the rectangle. Step 2, they're telling me to revolve it around the x-axis. So here's my x-axis right there, and here's my rectangle. And what do I notice about that? It is perpendicular. So if it is perpendicular, we're going to use the washer method. Okay, the washer method is going to be this formula. Now, what do you notice about this guy right here? The rectangle is actually touching my axis of revolution. So little r is going to equal to 0 because it's touching it. So I'm really going to be concerned with pi big radius squared dx. That's it. That's my formula. Now, the bounds is always going to be the area. The area from where to where is my area. My area is going to be from 1 to 4. So I'm going to have the integral from 1 to 4. So it's going to be 1 to 4. I have the pi. And now the only thing that I need is my radius. That's it. Now, what's the definition of r? R is going to be from step 1 to step 2. But sir, it's touching it. Nope. Remember, the little r is 0 because it's touching it. But what's my big R? My big R is going to be the furthest distance of that is the furthest distance of my rectangle. So this is my R. And now what's R? Well, I can bring in the little man, right? If I bring the little man right here, I'll put the little man right there. How much do I walk from here to here? Well, I walk up y. But what is y? Y is going to be determined by the function. And my function is going to be x squared minus 4x. So then all I'm going to do now is I'm going to insert my x squared minus 4x quantity squared, and I'm done. Okay, so now what I'm going to do is I'm going to do the exact same problem, but I'm going to be changing the axis of revolution. So this was the x-axis. In the second scenario, oops, I did it. Yeah. Well, I changed the function here also. Okay, in the second scenario, they want you to revolve it around the line y equals 5. All right, so here's my rectangle. This is step 1. Check. Step 2, highlight the axis of revolution. Check. I notice that they're perpendicular, so I'm going to put pi big radius squared minus little radius squared. Okay. Now, what's the only letter that I have, the only variable that I have in this function is the letter r. Well, there's a big R and a little r. This guy, he's going to be the furthest distance, and this guy is going to be the closest distance. Okay. So right here, I'm going to notice that this right here is going to be my little r, and this is going to be my big R. Okay. So now what I do is I bring in my little man. The little man is going to stand on, he always stands on the x or y axis. Now, please understand, did you notice how the braces are going up and down? Well, I'm going to put the little man on the x axis. Okay. How much does he walk from here to here? He walks y. But y is equal to 5. So that means that my big R is going to equal to 5. Now, the hard part is understanding the little r. How much does he walk from here to here? He walks 5. But this and this are not the same size, right? So then he's standing here again. How much does he walk from here to here? He walks the function. He walks the functional f of x, all right? So now, how do you find this piece? Well, you're going to take the big piece minus the little piece. So you're going to end up with 5 minus f of x. And I have to identify this guy as f of x. Okay? So now the big radius is 5. The little radius is 5 minus f of x. Plug it in, and you have set it up already. Okay? Let's try another one. We're going to take this exact area, and we're going to revolve it around the line y equals -1. So -1 is going to be down here. That is my axis of revolution. Here's my rectangle. I notice that it's perpendicular. Okay, so this guy is located at y equals -1. All right. Now, if it's perpendicular, we're going to use the washer method. Now, the washer method has a big R and a little r. So this guy will be my little r, while this guy here, this guy here is going to be my big R. Now, where does the little man stand? The little man stands on the x or y axis. So I'm going to put the little man right there. How much does he walk from here to here? He walks y. But y is -1. Oh, remember what I said. He cannot walk a negative distance. So he's going to walk. My little radius is going to be, little r is going to equal to 1. What about the big radius? What's my big radius going to be? My big radius, I'll put the little man right here. Okay. How much does he walk from here to here? He walks the function, he walks y. But the function is going to be my function, f of x, right? But wait a minute. This and the blue are not the same size. The blue is bigger. So I have to add the little piece down here. And that little piece we found out was 1. So big R is going to be my function plus 1. So I'm going to define this guy as f of x. Okay. So now I can substitute it into my formula. And I'm going to pi the integral from 1 to 4 of f of x plus 1 squared minus 1 squared. Let's try one more. Okay. Let's try it. Actually, there's 2 more that I got to try. Okay. Let's revolve the area around the y-axis. Okay. Step 1, draw the rectangle. Step 2, highlight the axis of revolution. Done. Now, what do you notice about the 2? They're parallel. And that double L is going to tell me that it's the shell. And the shell is going to be 2 pi RH. Now, what is the definition of R? R is going to be from step 1 to step 2. So this right here is my R. And then what is my H? My H is the height, which I said was going to be top minus bottom. And in this case, there's only the function, one function. So it's just going to be the function. So my height is just the function. Now, remember what I said. I bring the little man. Where do I put the little man? Well, I don't want to put him on the x-axis because if you notice, the R is left and right. So I'm going to put the little man right there. So there's my little man. How much does he walk this way? He walks a certain amount. I don't know what he walks. So I'm going to call it x. Somebody might say, hey, sir, why not call it 3.2? Well, I drew the rectangle there. Somebody might have drawn the rectangle over here. You understand? So we don't know where that rectangle is. But the x coordinate will always tell me where that rectangle is. So if I draw my rectangle here, I know my x coordinate will be 2. If I draw it right here, I know it'll be 1.5. You know, so my x will tell me where my rectangle is located. That's why we call it x. So that means that my R is x, and don't forget the 2 pi in the front. And I can put the 2 pi in the front because of one of the properties of integrals. All right. Let's go ahead and look at another one. In this scenario, I decided to revolve it around the line x equals 5. So here's my step 1 right here. Here's my step 2 right there. That's my step 2. And now I notice that they're parallel. So I'm still going to use the same formula. So what is R? R is going to be from step 1 to step 2. So this right there is my R. So where do I put the little man? I put the little man on my y-axis. How much does he walk from here to here? And he walks 5. He walks x, but x is equal to 5. So that's going to be 5. How much does he walk from here to here? He walks x. And we don't know where that rectangle is at, so we call it x. So then what is my R going to be? My R is going to be 5 minus x. And what's my height? We said the height is always top minus bottom. So in this case, it's just going to be f of x. Okay, let me go back and change this guy to f of x. All right, let's try one more. This is the last one that I do. This time, we're going to take the area and revolve it around the line x equals negative 1. So if you notice, step 1 is here. That's step 1 right there. This right here is step 2. So I put it outside that picture so you're not going to see it. So I notice they're parallel, so I'm still going to use the wash method. The shell method. And when I look at it, I need to know what R stands for. R is going to be from step 1 to step 2. So this is going to be the definition of R. Now, where do I put the little man? I put the little man on the axis. It has to be either the y or the x. How much does he walk from here to here? He's going to walk x. Now, this line and the red line are not the same. The red line is bigger. So I need another piece. I need to know this piece over here. How much does he walk from here to here? He's going to walk 1. So now if I combine these two together, guess what I'm going to have? I'm going to have R. So R is going to be defined as x plus 1. Okay? So now what's the definition of height? The height is going to be top minus bottom. So it's just going to be the function f of x. So let me put here f of x. And now we have x plus 1 times f of x. I don't know if that's my last example. Let me check. Yep, that's my last example. So that concludes the video on the washer and the shell method.